Assalamu alaikum. Welcome, dear students, to our third part in Chapter 15, Rectilinear Motion. By the end of this video, you will be able to determine the characteristics and time equations of uniformly varied rectilinear motion, UARM and UDRM. Let's start by reviewing together the main objectives of the previous video. We've studied that in a uniform rectilinear motion, the object moves on a straight path with a constant speed. If the object moves in the positive direction, then the VT curve is a horizontal straight line situated above the time axis, and the XT curve is a linear function with a positive slope, where x equal VT plus x0. Whereas, if the object moves in the negative direction, then the VT curve is a horizontal straight line situated below the time axis, and the XT curve is a linear function with a negative slope, where V represents the slope of the XT curve. Now let's move to the case of uniform varied rectilinear motion where the object moves along a straight path, but its speed varies with a constant rate. To achieve our objective, we are interested in plotting the AT, the VT, and the XT curves for uniform varied rectilinear motion, then deduce the time equations of motion, A as a function of t, V as a function of t, and x as a function of t. In the beginning of this chapter, we have recorded the instantaneous speed of a driver each 5 seconds. The speed increases with a constant rate, that is 3 meters per second each 5 seconds. Now, to plot the AT curve for a uniform accelerated rectilinear motion, we need to calculate the acceleration at different instants. A1 is equal to delta V divided by delta t, which is equal to V2 minus V0 divided by delta t. This gives us 6 divided by 10, which is equal to 0.6 meter per second square. Similarly, A2 is equal to A3 is equal to 0.6 meter per second square. It's clear that the acceleration remains constant since the speed increases in a constant rate. We plot the values, and the AT curve obtained is a horizontal straight line parallel to the time axis, showing that the acceleration is constant in a uniform accelerated rectilinear motion. Let's now plot the VT curve after choosing a convenient scale. When joining the points, we obtain a linear function, an increasing straight line of positive slope. The equation of the curve had the form of y equal ax, where y is the algebraic value of the velocity and x is the time. A is the slope of the curve, which is equal to delta V divided by delta t. The unit obtained is meter per second square. Then the slope represents the acceleration A of the motion. This implies that V equal to AT. Note that at t equal to 0, the initial speed was 0, then the driver starts from rest. But in the case where the object starts with an initial speed V0 different from 0, then the curve obtained will have the form of y equal ax plus b, where b is the y-intercept, which is the initial speed at t equal to 0. Then the equation becomes v equal at plus v0, where a is the slope of the curve representing the constant acceleration of motion, and v0 is the initial speed at the instant t0 equal to 0. Now we need to plot the xt curve for a uniform accelerated rectilinear motion. We record the positions after equal intervals of time, then we plot them. The curve obtained is a curvilinear parabolic curve whose equation is of the form x equal half at square plus v0t. Note that in this case we started timing when the object was at the origin of space, which means that x0 is equal to 0. In other cases, the general equation is x equal half at square plus v0t plus x0. Then, in a uniform accelerated rectilinear motion, the VT curve is a linear function of positive slope, and the VT time equation is V equal AT plus V0, where A is the constant acceleration which represents the slope of the VT curve, and V0 is the algebraic value of the velocity at the instant t0 equal to 0. whereas the xt curve is a nonlinear function and the xt time equation is half at squared plus v0t plus x0. Now let's recognize the vt curve of a uniform decelerated rectilinear motion. If the object starts with an initial speed v0, moving along a straight path, and its speed decreases with a constant rate, so its speed decreases linearly with time, then the vt curve is a linear function with negative slope, and its equation is written as v equal at plus v0, where a is the slope of the vt curve, which represents the acceleration of motion, and v0 is the initial speed at the instant t0 equal to 0. Then, in a uniform decelerated rectilinear motion, the vt curve is a linear function of negative slope, and the vt time equation is v equal to at plus v0, whereas the xt curve is a nonlinear function and the xt time equation is x equal half at squared plus v0t plus x0. Let's practice now by solving application 1, but before you start, please pause the video and try to solve the application by yourself. A racing car is traveling north. It accelerates uniformly, covering a distance of 725 meters in 10 seconds. If it has an initial velocity of 10 meters per second, determine its acceleration. Note that to answer this question, you need to follow 3 steps. In the first step, you need to identify what information is given and what information is asked for. Actually, you are given that v0 is equal to 10 meters per second, delta x, which is the distance traveled by the object, is 725 meters, and t is equal to 10 seconds, and you are asked to calculate the acceleration a. If you struggle to find the correct equation, you need to follow the second step. You need to find an equation of motion relating the given information to the unknown we are searching for, according to the type of motion. In the third step, you have to substitute your values and find the answer. Actually, the motion of the car is a uniform accelerated rectilinear motion. So, the best equation to use is delta x equal half at squared plus v0t. Since you have delta x, you have t, and you have v0, and you are only asked to calculate a. After substituting the values and performing the correct calculation, you will obtain that a is equal to 12.5 meters per second square. Then the racing car is accelerating at 12.5 meters per second square north. Let's move now to application 2 and try to apply the time equations of motion for a uniform varied rectilinear motion to real-life examples. Say you get into your car to drive to the supermarket. While the car was at rest, which means that v0 is equal to 0, you place your foot on the gas and apply a constant acceleration a equal 2.5 meters per second square. What will your velocity be after 10 seconds? The motion is a uniform accelerated rectilinear motion. You are given a, t, and v0. Then to calculate v, you should use the time equation v equal at plus v0. Substitute the values in it, and you will obtain that v is equal to 25 meters per second. Now, if you are asked about how far will you have traveled in that time, then you are asked about the distance x minus x0. X minus x0 is equal to half at squared plus v0t. You have all the other factors, you substitute them, and you will obtain 125 meters. Now, let's consider that the car is already in motion with a velocity of 27 meters per second. Let's say you need to stop suddenly, so you'll apply the brakes, initiating a rapid deceleration of a equal minus 8.4 meters per second square. What long does it take you to stop? The motion is a uniform decelerated rectilinear motion. The time equation you should use is v equal at plus v0. Substitute the values in it, you will obtain that t equal 27 divided by 8.4, which gives you 3.1 seconds. Now, in order for you to specify the type of motion, you should mention the following. In a uniform rectilinear motion, the trajectory is a straight line, the speed remains constant with time, the acceleration is null where a equal to 0 meter per second square, which means that a dot v is equal to 0. The time equations of motion you are going to use are x equal vt plus x0, where d is equal to vt. In a uniform varied rectilinear motion, the trajectory is a straight line, the acceleration is constant. If the acceleration and the velocity vectors have the same directions, which means that a dot v is positive, then the motion is a uniform accelerated rectilinear motion. And if a and v have opposite directions, then a dot v is negative, which means that the motion is a uniform decelerated rectilinear motion. The time equations in this case are v equal at plus v0 and x equal half at squared plus v0t plus x0. Let's summarize the ideas of this video. In a uniform varied rectilinear motion, the trajectory is a straight line. The instantaneous speed of the moving body varies with a constant rate. The acceleration is constant with time. The vt curve is a linear function. The xt curve is a non-linear function. And the time equations of motion are x equal half at squared plus v0t plus x0 and v equal at plus v0. Then, in a uniform accelerated rectilinear motion in the positive direction, the vt and the xt curves are as follow. And in a uniform decelerated rectilinear motion in the positive direction, the vt curve and the xt curve are as follow. This is the end of part 3. Thanks for your attention.